What's up, guys? We are going to work on impulse and momentum. Let me move my things around just a little bit. And when it comes to momentum, what I've said before is that momentum is always conserved. And that is true. If, and there's going to be an if in there, if the net force on the object is 0. So let me show you what I'm talking about. So if F net equals 0, then momentum is conserved. Oh, if I can write. Okay. And that tells us that momentum before any interaction is going to be equal to momentum after any interaction. What if F net does not equal 0? And usually, at least one person asks, well, if momentum is always conserved, then how does it get momentum? Let's say does not. Let's put a big does not equal 0. I'm like, well, then how does momentum ever get into an object if momentum is always conserved? And that's if F net equals 0. Well, if F net does not equal 0, then you have what's called an impulse. Impulse is just simply defined as a change in momentum. So we do that, write it as delta P. I have seen a couple of places on physics textbooks and things like that write it as J, but we also use J for joules, and I've seen that get some people confused. So I just don't use that. I just define impulse as the change in momentum. Okay, let's see what we can do there. Before we get there, let's do an example where momentum is still conserved and make sure we're all on the same pace. So I'm going to zoom out just a little bit because I'm probably going to need the extra space. So a 5 kilogram grenade is thrown on a flat field and explodes into 2 uneven pieces after rolling to a stop. One piece explodes with a mass of 3 kilograms and a velocity of 36. Determine the velocity of the other piece. So momentum before equals momentum afterwards. We then ask ourselves the question, how many objects are there before the explosion or before the collision? And that is 1. And so that's 1 grenade. So I'm going to put P sub G for the momentum of the grenade. After the explosion, we have the piece that's going to the left. So I'm going to put P sub L plus P sub R. One piece is going to go to the left, one piece is going to go to the right. Okay, let's determine the velocity of the other piece of the grenade. So what do we know momentum? Momentum is mass times velocity equals mass velocity of the left piece plus mass velocity of the right piece. You can put, I guess, L and R in here if you want to make sure all your variables are nice and straight. Okay, what is our total mass? So total mass is 5, but before then, it's the grenade's not moving, so it has a velocity of 0. The mass of the piece going to the left, so let's draw a picture now. I guess we should have drawn a picture to begin with. If I have a 3 kilogram piece going to the left, and we had 5 kilograms in total, then that means I have a 2 kilogram piece going to the left. So the mass of the piece going to the left is 2. We're looking for the velocity of the piece going to the left. Mass of the piece going to the right is 3, and that is with a velocity of 36 meters per second. Okay, so 0 equals 2VL plus 36 times 6. Where is my calculator? There it is. 36 times 6. It's going to be like 108. Is that right? I don't know. Let's just double check it. Anytime I try to depend on my mental math when I'm being recorded, I usually get something wrong. Looks good. Doing some quick math here. We're going to subtract 108 on both sides. So we get 2v equals negative 108. And so the velocity of the piece going to the left is going to be 54 meters per second, or negative 54 meters per second. Why is it negative? Well, this piece that was going to the right at 36 means that the other piece is going to be going to the left. And is it going to the left? Sure. So now it's going negative 54 meters per second. Cool. So we just did kind of a warm-up collision problem. Let's now look at impulse. There's going to be a video kind of attached in the description of this where Mythbusters goes through and they talk about this idea of an impulse and does momentum cancel out. So the idea of momentum cancellation is that if you have two shock waves from two different grenades on opposite sides of a person, do those shock waves cancel out if they were to explode at the same time? This is kind of a Army urban myth. I would say a very good one, but it's still one nonetheless. And they actually test it out. So I want you to ask yourself the question, is if there was a grenade, if you had two grenades explode at the same time, and somebody standing perfectly in the middle of those two explosions, would those shock waves cancel each other out? You tell me. All right. Now let's look at impulse and unpack that just a little bit more. So we said earlier, impulse is a change in momentum, and it's written with this funky stuff right here. So what we see is delta P equals F net delta T. So the change in the impulse of the system equals the force multiplied by the time that is experienced by that object. So if we look at this golf ball right here being hit by a golf club, an impulse or a change in momentum, because there's going to be a certain amount of force for a certain amount of time, is going to change that momentum of the golf ball from 0 to something. And how did it go from 0 to something? It was given an impulse or a force for some amount of time. Now, if we remember that delta P, that delta means change, so the change in momentum can also be written as final minus initial. Look at that, it's coming back on for it. And then we can then expand our formula out and say mass versus velocity final, mass versus velocity initial. And that's where the second half of this kind of equation comes from, is that if we were to really unpack it, you can see that an impulse is defined as the change in velocity, or as kind of predicated by the change of velocity. Okay, so let's try a couple of these questions out. Superman is attempting to stop a train with a mass of 3 million kilograms. You know what? I'm going to not do this question because it takes long to do and there's a lot of big numbers. Let's do a number that's a little bit more in the realm of doable. Here's what I wanted to show about this one, is that kind of how superheroes break physics. When Superman stops a train, and he stops it really fast in the movies because you don't want him to slow down the train really quickly. Or even like Spider-Man did this in one of the Spider-Man movies. Which one would that be? The one with Doc Ock in it. In any case, they both stop trains really fast. And what happens is that the problem is that the force you would need to stop that train that quickly, everybody would be ejected from the train because of how much force they would do on stopping that train. Or the train would crumple on itself. Another one is if you have somebody falling from a really high building and then a superhero comes by and catches them, their body would immediately decimate because in order to have that change in momentum really quickly, there would have to be a huge force, and so their bodies would just snap. Cool stuff. All right, let's work on this problem. How much force would it take to stop a 3 kilogram bowling ball rolling at 3 meters a second in 3 seconds? That's a lot. That's a mouthful. So what I want you to do is kind of write down what information we have. And now when it comes to momentum questions, ask yourself, is this a collision or is this an impulse question? Since we're looking for force, it's easily going to be an impulse question. So impulse, which is the change in momentum, equals force times the change in time. This is how it's written as the equation on one of my posters, that blue one up on the wall. Okay, well, change in momentum, which is going to be final minus initial, equals force times your change in time. All I did was expand this delta P into final minus initial. Since we're getting it to stop, how much momentum does it have if you want it to stop? And that final momentum would be 0. So we can say mass velocity final minus mass velocity initial equals force delta t. Well, final velocity is 0, so that's going to be 0, minus your mass is 3, initial velocity is 3, and force delta t is going to be 3 seconds. So negative 3 times 3 is negative 9. Divide both sides by 3. So the net force that this object is going to get is negative 3 newtons. And does that make sense? Well, I had an object, a bowling ball. So let's draw a bowling ball. So I got a bowling ball that was rolling to the right and then came to a stop. In order to make it to come to a stop, what direction would you have to push that force? That force would have to be going to the left. So it makes sense that our net force that we'd have to apply is going to be negative 3. Okay, let's try some more. How long force would it take to start? I'd say, how much force? Yeah, how much force? Look at me writing questions, my sleepy stupor. Okay, how much force would it take to start a 5 kilogram bowling ball at rest to be rolling 9 in 7 seconds? I want you to try this one out. Hit pause the video and see what you get. The same answer as me. Did you pause the video? I wonder if students actually do this or not. All right. Change in momentum or impulse equals force delta t. So we have final minus initial equals force delta t. Final is going to be, well, we got mass times velocity final minus mass times velocity initial equals force delta t. Mass is going to be 5. Final velocity is 9. Mass is 5. Initial velocity is 0 since it's moving at rest. We're looking for force, and that time is 7 seconds. So 5 times 9, that's going to be 45 minus 0 equals 7F. Divide both sides by 7. That's going to be some slightly ugly number. 45 divided by 7. So we get a net force of 6.43 newtons. So does that make sense? Does it make sense that it's positive? Well, we got a ball, and then after a while, the ball's going to the right. Well, in order to make a ball go to the right, what direction do you have to push it? And that force has to be going to the right. It has to be a positive force. Okay. I think we got one more. Yeah. We got one more, but this time we're looking for time. And we have 2 different velocities. So let's draw a picture for this one. So I got a bowling ball. Its velocity is 2. Its initial velocity is 2 meters per second. And its final velocity is 5 meters per second. What I want you to do is I want you to try this problem out, pause the video, try it on your own, see if you get the same answer as me. Okay. All right, delta P equals F net delta T. So that's mass velocity final minus mass velocity initial. I did skip that first step because I really don't think we need to do it anymore. Mass is 7. Velocity final is 5. Minus 7. Velocity initial is 2. We're looking for force again. And your change in time is 30 seconds. So this can be 35 minus 14 equals 30F. 35 minus 14, this can be 21 equals 30F. So we get a net force of to be, what's 21 divided by 30? I don't know, it's going to be like 0.6 something. Nope, 0.7. I was just off. 0.7 newtons. Does that make sense that it's positive? Well, yeah. In order to have the ball to speed up, the force on it needs to be in a positive direction. It's not going to be much, though, because the time of it pushing on it was actually a pretty large time. 30 seconds is a long time to push something. Okay. All right. I think that's going to be it, guys, for this notes. If you have any questions, feel free to reach out. And I will see you guys next week. Take care. Oh, where's my mouse go? There it is.